Hi, and welcome to the Mapping Real-World classes in EF Core 6 course. My name is Torben Jensen, and in this module and the following one we'll explore how to map .NET type hierarchies to a database using EF Core. When we want to map our .NET type hierarchies to the database, we have a couple of strategies that we can choose between. First of all, there's the table per hierarchy strategy. This was the first inheritance mapping strategy made available to us in EF Core. This was followed by table per type, which was introduced with EF Core version 5. And then, as per the release of EF Core version 7, we now have a third strategy that we can choose called table per concrete type. Other strategies exist, and choosing which one to use may also be impacted by the database system on which we run. But the three strategies mentioned here are all supported directly by EF Core. In the rest of this module, we'll dive into how we can use the table per hierarchy strategy for mapping type hierarchies in our .NET entity types onto the CardRock SQL Server database. In the next module, we'll focus on table per type and table per concrete type, and also address some pros and cons with the three strategies mentioned here. The focus of this module will be on the mechanics of the various mapping strategies, and we'll cover topics such as which schema each strategy leads to on the database and how this affects the queries that EF Core generates for us as we query our data. Some things, however, such as which implications choosing one over the other has in terms of storage and performance, will not be covered in detail. We'll touch upon these topics, but if you'd like to dive deeper into them and at the same time learn about mapping type hierarchies with EF Core straight from the horse's mouth, I suggest that you check out this recording of a live stream from the EF Core team. In this episode of the .NET Data Community Stand-Up, they look at the various strategies that we'll look at in this module and also offer advice on when to use each strategy. Before we start digging into the three strategies, let's take a look at the model that we'll be mapping to the database. In the previous modules, our data model didn't distinguish between various types of items for sale on the CardRock website. Everything was just an item. But in the real world, of course, things are not so simple. So our friends over at CardRock have introduced a few subcategories that each have different characteristics. What we see here is a simple model showing the new types of items that they have introduced. As we can see, the item entity still exists, and certain items that can be purchased on the website still have that type. These include the two items that we know from the previous modules, which are now considered to be uncategorized items. But now the item entity also acts as a base class for other types of items. Here we have the magazine item entity, which is derived from the item entity, so it has all the properties that we know from that entity. In addition to those, it also has a publication frequency property, which is used to specify if it is published on a weekly, monthly, quarterly, or yearly basis. Similarly, we now have a clothes item entity, which has a property specifying which fabric the clothes are made of. And then we have the food item entity, which has a date of expiry property. And as we can also see, it has a little star next to it, which is there to indicate that this is an abstract class, so we can't create any instances of it. Instead, that class is used as a base class for the dried food item entity and the canned food item entity. Both of these food item types have a production date, and the canned food item entity also has a property that specifies which material the can is made of. Creating .NET type hierarchies is probably fairly well-trodden territory for many of us, but the interesting thing here is of course which mapping strategy do we choose to map this model to the database. And that is the focus of the rest of this module and also the following module, where we will investigate the table per hierarchy, the table per type, and the table per concrete type strategies, and also see them in action. The first strategy that we'll look at is the table per hierarchy strategy, which is also known as single table inheritance mapping, because it uses a single table to store the data for all entity types in the inheritance hierarchy. That means that it stores entries for both the base entity type as well as all the derived entity types that exist in the hierarchy. Table per hierarchy is the simplest and in many cases the most optimal mapping strategy that we can choose, and it is also the default strategy which EF Core will use for mapping our type hierarchies unless we explicitly state that we want to use either table per type or table per concrete type. When we use this strategy, each entry stores the data relevant to its type in the mapping table, and a discriminator column is used to identify which type each row represents. The discriminator column is automatically created for us by EF Core. The discriminator column is the key to how table per hierarchy works. It can either be configured explicitly by specifying its type, its name, and which values are used to identify each of the types in our inheritance hierarchy, or we can let EF Core do the work for us. The discriminator property can be set up on our entities using EF Core's Fluent API, and can be configured like any other property to specify things such as max length, default value, and so on. If we do not explicitly configure the discriminator, EFCore will set it up as a shadow property on the base entity of our type hierarchy. But if we prefer, we can instead explicitly create a property on that entity and tell EFCore to use that as the discriminator. There are a few things that are worth noting about this strategy. First of all, using the table per hierarchy strategy will eventually lead to a lot of empty columns as our inheritance hierarchy evolves. This is because the mapping table will contain columns relating to all the types that exist in the hierarchy, and many of these might be specific to only a single or a subset of types. This preponderance of type-specific columns might eventually lead to a rather cluttered mapping table, which contains a lot of columns, several of which will only be used in a few cases and will be null in all other cases. But as we shall discuss later, that could easily be a small price to pay for the flexibility and ease of use offered by the table per hierarchy strategy. And it's also worth noting here that the performance issues related to having all these extra columns filled with null values will most likely be negligible. If, however, we are concerned about having several empty columns and what that might do to our performance, we can consider using SQL Server sparse columns. These sparse columns are optimized for storing null values by reducing the amount of space taken up by such a null entry. Using them does, however, come at the price of increased overhead for retrieving non-null values, so they should only be used in cases where doing so will lead to a significant reduction in the space taken up by the table's data. Another thing worth noting is that whenever we change the inheritance hierarchy by making changes to an existing entity or adding a new one, we'll also need to update the mapping table in the database because new columns must be added to accommodate new properties. This might initially not be such a big deal, but as our table grows, as more and more entries are added, making changes to its schema will take more and more time. And then something that we might not run into so often, but which could be relevant to know of as we are building our .NET type hierarchy, is that we might want to take advantage of some mapping features that are available to us when we're working with sibling entities. Sibling entities are entities that exist at the same level in our type hierarchy, meaning that they are derived from the same base class. For example, the canned food and dried food item entities, which are both derived from the food item entity, are examples of sibling entities. And if such sibling entities have properties with the same name, EFCore will default to mapping these properties to separate columns. That might very well be exactly what we want, but if these properties are of the same type, we have the option of telling EFCore to map them to the same database column, simply by specifying the same name for them using the hash column name method when we are configuring the entities. Such a column, which is used for several sibling entities, is called a shared column, and we shall take a look at these during the upcoming demo when we look at the production date for the two types of food item. For whatever reason, the CarvDog team decided to place the expiration date on the food item base class, but gave each of its two subclasses its own production date property. This is fortunate for us though, because it makes the production date a good candidate for exploring the shared column functionality. And finally, a reminder that applies to whichever of the three strategies we might choose. No matter how many entity types we define as part of our inheritance hierarchy, only those which we include in our data model, in our case the CarvDog database context, will be mapped to the database. This will be especially apparent if we're working with the table per type or the table per concrete type strategies, because when we use those, specific tables will be created for the types in our model, but it applies equally to all three strategies. Before we look at the table per hierarchy strategy in action, let's consider our model in the context of using that strategy. So what we see here is a slightly compressed version of the model diagram that we just looked at. And now we need to map that model to the database using the table per hierarchy strategy. And as we already discussed, that strategy maps all entities in the inheritance hierarchy to a single table like the one that we see here. Actually, the CarvDog team decided to build upon the existing item entity. So what we see here is in fact the existing items table from the database, which has been extended with several new columns. This is a simplified version of the actual table, but it illustrates the characteristics that we've just talked about. For example, here we see the discriminator column, which tells us what type of entity each entry must be mapped to. Here we can see the various types of items that we looked at before, such as canned food and clothes items. We can also see a type here named uncategorized item. This is not actually a type in our data model, but EFCore allows us to specify custom discriminators for our types. And this has been done for the item base entity, as we shall soon see. The rest of the discriminator names that we see here are default values created for us by EFCore. The first four columns that we see here are all mapped to properties that already existed on our item entity. So they are not new and they look exactly like they did before we started to implement the table per hierarchy strategy. But the columns that we see here are all new. and are used by EF-Core together with the discriminator column to correctly map all the relevant entity types. So for example, here we have a can of tomato soup, which is obviously a canned food item. This item has certain characteristics, such as what material the can is made from, when the product expires, and when it was produced. And as we can see here, all the columns for these properties are filled out for this entry. But other columns, such as the fabric and publication frequency columns, which are mapped to the clothes item and magazine item entities respectively, are null. Conversely, the next entry is a pair of hiking shoes, which is a clothes item, and thus has no information about canning material or expiry and production date, but instead it contains information about the fabric from which the item was made. And then of course there's the knotting rope which we see here, which has no information in any of the new columns. This is because it is mapped to our original item class, which is indicated here by the uncategorized item type discriminator.